Hello, I'm Brian Young. Today we're doing 26204 conduit bending. Let's get started. 26204 conduit bending. Successful completion of this module prepares you to identify the NEC requirements for conduit bends, identify the minimum radius requirements for various types of conduit, calculate the number of bends per run, use equations to find bend distance, demonstrate how to use mechanical benders, demonstrate how to use electric and hydraulic conduit benders, and demonstrate how to install PVC conduit. And of course, there are performance tasks that you'll do with your instructor. The installation of intermediate metal conduit, rigid metal conduit, and electrical metallic tubing often requires many changes in direction in the runs, ranging from simple offsets at the point of termination to complicated angular offsets at columns, beams, and similar obstructions. This module describes how to make conduit bends using mechanical, hydraulic, and electric bending equipment. I kind of preliminarily took a look at this module, and I think it's going to be a long one. It might be 5 videos. I'm going to try to give you the information you need, but not to drag it out. So here's a highlight. It says the installation of intermediate metal conduit, rigid metal conduit, and electrical metallic tubing often requires changes of direction along the path from a simple offset at outlet boxes to complex regular or angular offsets at columns, beams, and other obstructions. An offset is 2 equal bends made to avoid an obstruction blocking a conduit. We'll see that when we get to it, and I'll go to the magic board and draw some things. Let's see here. It says, unless the contract specification dictate otherwise, changes in direction, particularly in the case of small conduit sizes, are made by bending the conduit. For larger conduit, changes of direction are sometimes accomplished with the use of a factory-formed elbow. So if you don't have a 4-inch rigid bender, some contractors don't, they have up to 2-inch. If you're running 4-inch, you just buy 90s and 45s, a 90-degree or other angled bend, often abbreviated and spoken as L. So it's an elbow, it's a 90-degree bend. And like I say, you can also buy 45-degree bends in rigid conduit. It costs more than just straight conduit, but it costs a lot less than a 4-inch rigid bender. So, on-the-job conduit bends are also performed when installing multiple runs of the larger conduit sizes. It's easier to maintain true parallel alignment of multiple run using on-the-job conduit bends rather than factory elbows. Such bends can be made from the same center using the bends of the largest conduit in the run as the pattern for all the other bends. They want to try to call that concentric bends, but they're not true concentric bends. True concentric bends, the radius continues to increase from the center focal point so that all of the conduits are running on the same center line. But the radii get larger as you get further away from that focal point. Minimum radius requirements. NEC Chapter 3 contains the installation requirements for various types of conduit. Article 344 is related to rigid metal conduit. And Article 344.24a requires that all conduit bends be made so that the conduit isn't damaged and the internal diameter of the conduit won't be reduced in size. You cannot kink the pipe when you make a bend or a 90 in it. You need to use the right equipment and know how to use it and keep pressure on the pipe in order to maintain the proper diameter internally. You don't want to crush the pipe. You don't want to egg shape the pipe. The code book goes on to say that if you do egg shape it, the cross-sectional area is going to be used in the smallest diameter. So if you happen to make the conduit, let's just say 2.5 inches by 3 inches, by egg shaping it, you're only going to be able to use 2.5 inches for your mathematical calculations for conduit fill. It says, measured to the center line of the conduit shall be not less than that listed in NEC Table 9. I'm sorry, Chapter 9, Table 2. Let's take a look at Chapter 9, Table 2. It tells us the minimum bend radius for certain conduit. So if we go into our table of contents, we'll see that Article 344 is rigid metal conduit, page 232. Let's go down to page 232 and take a look at bends how made. So here's Article 344, rigid metal conduit in the code book. And if we go to part, I think it's, here it is, Article 344.24. I think it's in part 2. Well, it doesn't matter what part, but it's in part 2. How made? Bends of rigid metal conduits shall be made so that the conduit will not be damaged and so that the internal diameter of the conduit will not be effectively reduced. Radius of the curve of any field bend to the center line of the conduit shall be not less than that indicated in Table 2, Chapter 9. So I looked earlier just to see it's on page 719, at least in this. And there we go. Let's see here. We're looking in Chapter 9, Table 2. While we're in Chapter 9, we'll take a look at a couple of different things. So here's Chapter 9. It's tables and examples, basically. And Table 1 gives us conduit fill. If we have one conductor in a conduit, we're allowed to fill that conduit cross-sectional area up to 53%. If we have two conductors, we can only fill it to 31%. And over 2 is usually what we electricians are going to do. We usually have at least 3 conductors in a conduit, so we go with 40%. That's just for your information. We're not really doing conduit fill right now. But here's Table 2, the radius of conduit and tubing, and again, it's measured to the center line of the conduit. So it tells us that a 1/2-inch trade size EMT or rigid has a minimum radius bend of 4 inches, 3/4 is 4.5, a 1 inch is 5 3/4. So they give you that information in Chapter 9, Table 2. They tell you what the minimum bend radius can be for that conduit. All right. Know the code. There's the center line. Whenever we're talking about an 18-inch radius, 90, we're measuring to the center line. The reason for that is because the conduit is least affected at that center line. The metal on the outside of the bend is going to be stretched to be longer, and the metal on the inside of the bend is going to be compressed and become shorter. It actually changes the internal structure of the conduit. The conduit is metal, it's malleable, and as we bend it, as we coin that bend, we will stretch the conduit, the metal over here, and we will compress the metal on the inside of the bend. So we always measure to the inside of the pipe, the center of the pipe, center line of the pipe. There's a nice 90-degree bend in what appears to be 1.5-inch conduit, just looking at it. There's good reason to follow the bend radius requirements laid out in Chapter 9, Table 2. When bends are too tight, the conduit's distorted, pulling wire becomes difficult, and the insulation on the conductors can be damaged. So it's all about keeping the insulation and the wires themselves in good working order. We don't want to fight the wires to get them in. A lot of times you can stretch or even break strands of the copper conductor inside the wire, stretching the insulation, and you don't know it, but it's a hot point inside the cable run. So we don't want that to happen. Number of bends, 360 degrees. Here's a highlight. The NEC specifically states that no more than 360 degrees of bend. It says 4 90-degree bends. They call it in the code book 4 quarter bends. May be made in a single conduit run between outlet boxes, cabinets, panels, junction boxes, or pull points. So if you're running a long run of rigid conduit or EMT, and you get to where you have 4 90-degree bends or any number of bends that add up to 360 degrees, you need to put a pull point. You can put a conduit, you can put a C conduit, just a pulling conduit, and then continue on with your pipe run. You can put a box, you can put an LB or LL or LR. You can put any kind of a fitting that has a cover that can be taken off, and that's a pull point. An elbow or L is a 90-degree bend that's used when the conduit must turn at a 90-degree angle. Two elbows are often used to create a back-to-back bend. In single conduit runs, when the larger size of conduits are being installed, factory elbows are frequently used to save labor on setting up equipment, calculating making the conduit, and finally making the bend. However, in multiple conduit runs, a neater job will result in on-the-job multiple sets of sweep bends. So here's a sweep bend. They're actually figuring what the radius of their bend, what they want, and then they're measuring between the bends. And here they're putting 6, 7, 8, 9, 10. They put 10 9-degree bends in this conduit. I think I would have chosen to make 9 10-degree bends because it's easier to see 10 degrees on a protractor. But then this one, they're spacing the bends further apart in order to increase the radius of the center line of that conduit. So here's our focal point, and there's a shorter radius to center of this pipe. Then we add 2.5 or 3 inches, whatever we want between them, center to center. You measure that one, and then you add another 3 inches to this one, and another 3 inches to this one. Probably 3 inches is not enough to go center to center. You want the conduit plus at least an inch. Some places will tell you 1.5 inches. So if we're using 2-inch conduit, we want these to be at least 5 inches center to center to give us 2 inches between our conduit, 2.5 inches. The outside diameter or the outside measurement of this 2-inch conduit would be 2.5 inches roughly. All right. So that's what they mean about using sweep bends on the job. They look neater, it's more professional. You can line your couplings up. On this one, they're using factory 90s, and they're not concentric, meaning they have different focal points that the radius of the bend is centering around. So they're not concentric. You have more space here at the 90 than you do on the straight pipe. And yeah, it gets the job done. If your contractor's more concerned with money than with aesthetics, they won't want you to take the time to make these sweep bends. But look how nice that looks with the same distance between the bends all the way around the 90. That's a lost art, doing concentric bends. An offset. An offset consists of 2 equal bends that is used when the conduit must run over or go over something or around an obstacle. Basically, an offset is a change in elevation, but not a change in direction. So if you put a 45-degree bend in this first bend, you're going to make another 45-degree bend that rotated 180 degrees on the center line of the conduit in order to go back to being straight. If we were traveling east a minute ago, after the offset, we're again traveling east. It's not a change in direction. It's a change in altitude. It's a change in height. A saddle, it says both 3-bend and 4-bend saddles can be used depending on the type of obstruction. Saddles are used to cross a small obstruction or other runs of conduit. A saddle is made by marking the conduit at a point where the saddle is required and then placing the bends a few inches ahead of this point. That's a box offset. So here they're making a 4-bend saddle. It not only is not a change in direction, it's not a change in elevation. It goes over the obstruction and comes back down to the same level it was on a minute ago. So if you're running on a ceiling or a wall and you have an obstruction you need to go around, you can make a 4-bend saddle, and again you'll be back on that same wall or ceiling. So if My understanding is if you're going over a square or rectangular obstruction, you want to use a 4-bend saddle, and if you're going over a round obstruction, you want to use a 3-bend saddle. The 3-bend saddle is made by making one bend in the middle that's twice the degree of the bends on the outside. So if this is 45 degrees, these two will be 22.5 degrees. If this is 60 degrees, these two would be 30 degrees. Most often I like to use 22.5, 45, and 22.5. A kick is any single change in direction less than 90 degrees. So here's a kick. Sometimes you need to do that just to get the pipe going away from an obstruction, or if you need a 90 to go into a box and the box is off the wall, you might kick and then put the 90, and then it'll be elevated off that wall. So there. Says some electricians believe that offsets, kicks, and saddles are not bends, especially in areas where the electrical inspectors are lax. These electricians count only those bends that are 90 degrees. The misconception of this is quickly apparent when wires are pulled. I had an inspector one time. He'd count every offset as 90 degrees. And I tried to argue with him. I said, it's two 30-degree bends, so it's only 60 degrees. No, every offset is 90 degrees. So he counted every 90 as 90. He counted every offset as 90. Even a box offset he counted as 90. And he said I was over the 360 degrees and I needed to put a junction box in the middle. So I did as he instructed, and I put a box in the middle. And then he came back and we passed inspection. So many electricians prefer to install a pull box at closer intervals to reduce the number of bends, especially when larger conductors are to be pulled through. Pushing the limit to 360 degrees is not always desirable or necessary. The additional cost of the pull boxes and the labor to install them is often offset by the labor saved in creating bends and pulling the conductors around multiple turns. So remember that. If you can put a box in a convenient place, it's better to do that than to make a lot of fancy bends. If you're making several 4-bend saddles in a conduit run, you're better off just putting junction boxes where you need them. For every size of conduit, there's a single minimum bend radius that must be maintained. False. No. You can always go better than the code. If it says a half-inch EMT has to have a minimum of a 4-inch radius bend, you can make a 12-inch radius or a 16-inch radius. You can segment bend that EMT and make it a larger radius bend. The type of bend required where conduit enters a panel board is most likely a box offset. A little offset, very small in size. It just gets it to where it's coming into the box in a straight manner so you can get the lock nut or the connector on. Bend distances. Use trigonometry to find the distance and use the circumference of a circle to determine bend distances. Okay. Trigonometry, don't be afraid. Finding bend distances with trigonometry. When I teach trigonometry, the first thing I say is an octagon has 8 sides, a pentagon has 5 sides, a hexagon has 6 sides, a trigon has 3 sides, like a tricycle, has 3 wheels. A trigon is a triangle. Geometry is the art or science of measuring. Geometry is the art or science of measuring the earth, geo. Trigonometry, trigonometry, is the art or science of measuring triangles. That's all it is. So don't let it intimidate you. Basically, we have a base, we have an altitude, and a hypotenuse. And if we're using 30 degrees, it's easy. The hypotenuse is going to be twice the height of the obstruction. If we have a 6-inch obstruction and we're bending our 2 bends on 30 degrees, we're going to put twice that 6 inches. We're going to put 12 inches between the center lines of the bends. And we'll get a nice 6-inch offset, and it'll clear the obstruction. All right. Right triangles used to develop trigonometric equations. These equations can be used to determine the rise or stub-up distance between both bend points. The distance between bend joints, the distance a kick needs to be above the surface, or the amount of additional conduit required. 6 basic trigonometric functions will be required: sine, cosine, tangent, cosecant, secant, and cotangent. Basically, 1 over the sine is the cosecant, 1 over the cosine is the secant, and 1 over the tangent is the cotangent. The sine function can be computed by dividing the hypotenuse by the side opposite the angle being considered. So sine is opposite divided by hypotenuse. Cosine is adjacent divided by hypotenuse, and tangent is opposite divided by adjacent. Really, those are the only 3 you actually need to know: sine, cosine, and tangent. All right, let me give you a crash course here. I don't like their explanation, but let's just very quickly take a look at what they're talking about. So we're going to determine where we are. Like when you go to the mall and they have that sign that says, "You are here." So there's the arrow pointing to this angle. This angle is where we are. This is called theta. It's just a name. Theta is the angle from which we are looking. In fact, we could draw an eyeball right here. And that eyeball is looking from theta. And the side that's opposite from where we are is called the opposite side. And the side that's touching where we are is called the adjacent side. It's adjacent to us. Adjacent. And then the longest side is always known as the hypotenuse. Okay, so this is theta. And I had a student show me once that theta is wearing a baseball cap. This is theta. And he's looking. So here's theta, and he's looking at this triangle. This is the opposite side, this is the adjacent side, and this is the hypotenuse. So we have these different sine, cosine, tangent. And sine is the opposite side divided by the hypotenuse. I did put my equal sign, there we go. Divided by the hypotenuse. And cosine is the adjacent side divided by the hypotenuse. And the tangent is the opposite divided by the adjacent. So if the sides of my triangle measured 3, 4, and 5, I would have a sine of 3 over 5, 3/5. That would be my sine for this theta right here. And my cosine would be 4 over 5. So 0.8. So this one is 0.6. Oops, let me use blue. Equals 0.6. This one equals 0.8. Oops, I'm talking as I'm writing. Sorry. This is 4 divided by 5. The hypotenuse is 5. So my cosine is 0.8. 4 divided by 5, 4/5. And my opposite over my adjacent is 3 divided by 4. So 0.75. So those are the 3 different measurements for sine, cosine, and tangent. 0.75. So sine is 3/5, cosine is 4/5, tangent is 3/4. Opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. And it's just a ratio, and every angle has a different ratio. If we're talking about 30 degrees, uh, 30 degrees has a sine of 0.5. So if my theta is 30 degrees, then my opposite side is going to be 1/2. Let's say it's 6 inches. This hypotenuse is going to be twice that. It's going to be 12 inches between my bends. And that's what we're talking about. We're talking about bending conduit. We're talking about how far apart to make our bends in order to make this 6-inch offset. So height of the obstruction times 2, and that'll give us our 12 inches. That'll give us the distance between those bends. All right. All right, let's get back to it. That's enough for now. So here they're doing that. They're saying that they have an obstruction that's 12 inches, and they're multiplying 12 times 2, and they're getting 24 inches as the height, or as the hypotenuse is 24 inches. So here they're asking us what the opposite side is. Well, if the hypotenuse is 20 inches, then this is 1/2 of that. It's 10 inches. The height of the obstruction is 10 inches. That's what they found out there, 10 inches. All right. And these equations also apply to metric. We don't do metric. So if you're somewhere where you do metric, I apologize. Metric is a great system. It really is. I have a lot of respect for it. I'm an old man. I'm never going to be comfortable with it. I know 12 inches in a foot, 3 feet in a yard doesn't make any sense at all when you have 10 decimeters in a meter, and you have 1,000 meters in a kilometer or a kilometer. It all makes perfectly rational sense. A circle is defined as a closed curve with whose points are all the same distance from the center, what they call the focus. The focus. And when we can bend different conduits and have all of their foci, their focuses, the same point, they're called concentric. And that is very pleasing to the eye. It takes a little bit of practice. Once you learn how to make concentric bends, you look like a master craftsman. A circle can be divided into 4 equal quadrants, as shown in figure 9. Each quadrant accounts for 90 degrees, making a total of 360 degrees. So a 90-degree bend is based on 1/4 of a circle. If we take that diameter times pi gives us the circumference, or the radius times pi gives us half the circumference, or we could say radius times half of pi would give us the developed length for 90 degrees of this circle, for 1/4 of this circle. So either it's 2 times the radius times pi for the whole 360, or the radius times pi for 180 degrees, or the radius times half of pi. Pi being 3.14, half of it is 1.57. So if we multiply the radius to the center of the pipe times 1.57, it'll tell us how much conduit we're going to use in order to coin that bend. So that's what they're doing here, the developed length. When calculating the circumference of a circle, the following formula is used. The circumference equals 2 times pi times the radius. So any number multiplied by 1 is equal to that number. So what are they saying? The radius is 1. Okay, so the radius is 1. So if we multiply times pi, we're going to get 180 degrees. And if we multiply times half of pi, we're going to get 90 degrees of that, the arc of that circle. So 1.57. There you go. Pi divided by 2 is 3.14 divided by 2 equals 1.57. I've now made that a highlight. 90 degrees is represented by the numerical value 1.57 times the radius. So with that in mind, if you multiply 1.57 by the given radius, it'll provide the linear distance from 0 to 90 degrees on the circle, or what we call the developed length. It will give you the developed length. So they're saying that they have a 2-foot radius times 1.57. They're ending up with 3.14 feet, and that's the developed length. And there we go again with metric. All right. So gain, yeah, all right. Let me go to my magic. Let me go to the 3DBB. Did you ever find out where that was from? So, all right. Sorry, I said I was going to try to be succinct, and I'm not being succinct. I'm taking my time and having fun with this. But there's a farm, and here's the road leading to the barn. And these two brothers, there's one in the pickup truck on the road. There's a pickup truck. I know, it looks a little bit awkward. I got the wheels a little too far out. And then the other brother is on the tractor. He's here in the field. He's in the tractor. And I don't know their names, but there they are. And we'll say Bob and Jim. So Bob says to his brother Jim, "I'll race you to the barn, knowing that the truck is faster than the tractor." So he goes down to the stop sign, he turns, and he goes to the barn. Well, old Jim is a little bit smarter than that. So let's see if I can group these together there. And he doesn't go in a straight line. He comes on an angle, and here, let me make it, here, I'll make it a weird color. He goes like this, and he beats his brother Bob, who's in the faster vehicle, because he went a shorter distance. That's gain. That's gain in a nutshell. Gain. Gain is when you measure a conduit and you say, this conduit is 24 inches, and this other one is 18 inches, and the two of those are 42 inches. But you started with a piece of conduit that was 39.5 inches. And it looks like you gained 2.5 inches, but you didn't. You used it up in this space right here. This is where your gain went. You don't really have a piece of pipe that's 24 inches and 18 inches. You have a piece of pipe that's, let's say, 20 or 18 inches. And then there's a developed length, and then the other piece of street pipe. So you used less pipe in order to get there. You cheated and you got to the barn before your brother Bob. That's what gain is. Gain is when we measure that 90 in straight lengths, and then we subtract the gain. It tells us how long this piece of conduit really is. It's really 39.5. It's not 42. So, all right. That's my best explanation of what gain is. Gain is the distance saved by producing a bend. There you go. So they have a gain factor. We won't worry about it. For a 90 degree, it says 0.4292 times the radius. That'll give you the gain. All right. So the gain for a 90-degree bend is found by multiplying the radius of the bend times 0.43, rounded up from the value of 4292. So 0.43 times the radius of the bend will give you the approximate gain. So this is saying that for 2 feet, it's 0.86 feet, or it's 10.4 0.32 inches, or 10 3/8 of an inch. Okay. Yeah, I always do degrees. I don't do radians or gradients, so I'm just going to skip this part. Always make sure your calculator is set to degrees. Applying math to a 90-degree bend. The desired rise or stub up and the take up or the deduct, the amount that must be subtracted from the desired stub length to make the bend come out correctly using a point of reference on the bender or the bending shoe. So we use bends, they've got here, they're converting fractions to decimals. And you can do this in your calculator, you can do it on a piece of paper, you can divide 1 divided by 64, and you'll come up with this answer, 0.015625. Or if you divide 1/8, divide 1 divided by 8, you get 0.125 when you do it longhand or in your calculator. So this whole chart is just making conversions from fractions to decimals. All right. Decimal may be mathematically converted to a fraction. To do this, remove the decimal point from the number, which then becomes the numerator, the top of the fraction. The denominator is always a 1 with as many zeros as there are decimal places in the decimal number. So if you got 0.75, it's actually 75 100ths, and it's 3/4. 0.375 is 375 thousandths, or 3/8. All right, that's converting. Back-to-back bend. Wait, we didn't explain a 90 yet. Well, okay, all right, that's right. We're not doing hand bending, so we're not going to worry about it. We've already had hand bending, I think, in 00107 or 26107, I think. All right. But here's a 2-foot length of pipe and a 4-foot length of pipe and a 3-foot length of pipe. So we have 9 feet of pipe. 2 and 4 is 6 and 3 is 9, except that we have 2 gains. So we have to subtract twice the gain. If they tell us the gain is 2.5 inches, we'll subtract 5 inches from our 9 feet, and we'll end up with 8 feet, 7 inches. Let's see what they came up with. 9 feet minus 5 inches of gain, because we had 2 90s. Each 90 is 2.5 inch gain, so we ended up with 8 foot 7 inch. And they're saying that you can cut this pipe beforehand and then bend your 90s. I never did that. I would always just bend the 90s first and then cut it off at the desired length and thread the conduit if that's what you need to do. All right. When applying trigonometric functions to conduit bends, the distance between bends is represented by the triangle's hypotenuse. And the gain for a 90-degree bend with a 6-inch radius, well, we do 6 times that 0.43, excuse me. So they're saying 6 times 0.43, and they're saying it's about 2.5 inches, 2.58. 2.58b. All right. I'll stop the video here and I'll start another one. All right. See you on the next.